Welcome to qnawire.
Here you have a body that's moving with a velocity of 5 meters per second. And this body, you're told it weighs 90 kilograms. And there's another body that's moving up that's 95 kilograms, and that's moving up at 3 meters per second. And there's a collision that happens here in the form of a tackle, and they tell you that afterwards, so after this collision happens, these two bodies stick together and they move with some velocity at some angle that's equal to VF in this case. So the first question they ask you is this, so what makes this a perfectly inelastic collision? And the answer to that is every time the two objects stick together here, that is what constitutes a perfectly inelastic collision, because you're going to lose some of your mechanical energy as these things get stuck together and move with a common velocity here. So they don't rebound off of each other, but they actually stick together and become one body as they move. So that's a perfectly inelastic collision. So now the second question they want to ask you is calculate the velocity of this thing after the collision happens. So the way to do that is, again, since this is still a collision, we want to always remember that PI is equal to PF. So in this case, again, since it's a two-dimensional problem and these are vectors that we're working with, we have to split it up into two different components as well. So if I start by doing the x direction, I'll realize that the only body that's moving in the x direction initially is this first mass here. So essentially that would just be m1 times v1I should be, because this is now 0 in x, that should be equal to m1 plus m2, all of this multiplied by the final velocity, but in the x direction. So you notice now that you have the m1, you have the v1, you have m1, you have m2. So essentially your solution is going to be m1 v1I over m1 plus m2 here. And all of that will give you the v final in the x. So if you plug in the numbers 90 here and 95 and 5, you see that your final velocity in the x direction is somewhere around 2.43 meters per second. So then you go ahead and do the same thing in the y. Again, this is the only body that's moving in the y. So now it's actually m2 v2I is equal to now m1 plus m2, this multiplied by v final, but in the y direction. And again, you do the same thing. You realize that m2 v2I over m1 plus m2 is equal to v final in the y direction. And you plug in 95 here, 90 here, in 3 meters per second, you find that is something around 1.54 meters per second. So these are the components of the velocity, but you want the vector itself. So to find the final velocity vector magnitude in this case, you're just going to do the square root of vfx squared plus vfy squared. And when you plug in these numbers in this formula here, you find that your final velocity comes up to something like 2.87 meters per second. And then for the angle, because again, these bodies are traveling in two different, essentially one is going up, one is going sideways. So we expect that maybe this will have like a final velocity along that direction. So then the angle that this makes with the horizontal now is what you want to calculate. And to calculate that, if you know the x velocity, you know the y velocity, right? And you know the x velocity. So you want the resultant velocity here. And notice to get this, what you call the hypotenuse side on this right triangle, if you were to move this over here, you have the adjacent opposite side, you have to use a tangent. So the tangent of theta will give you Vy over Vx. But we want to find theta. So to find theta, we're just going to do the inverse tangent of Vy over Vx. And that should give us the angle here. And if you take Vy to be 1.54 and Vx to be 2.43, and you put it in inverse tangent formula, you find that your theta is around 32.4 degrees. So this is your angle, that's the speed, and together these two form the velocity vector. And then the last part of this problem wants you to calculate the change in mechanical energy, or to calculate the energy loss in here. So if you want to find that change in energy, again, we're just going to do Ki minus Kf, or whichever one is larger, so you can get the magnitude if you want. So we know that there's no change in potential energy here because this thing is essentially just moving on the same plane, essentially. So there's no vertical motion. So we know the initial velocities. So this is half v1 squared plus half m2 v2 also squared. And that should give you something around, so if you plug in the mass 90 here, 5 here, 95, 3 here, you get something around 1500.5 joules over here. And then, so that's for Ki. And now to calculate the Kf, since they stick together, they have a common velocity now, but their mass is combined. So this would be m1 plus m2 times the velocity found. But this is the magnitude of the velocity because we're going to square it in this case. So once you square that, multiply by the sum of the masses, you get something around. So once you subtract that, whatever you get here, you subtract it from this guy here, and then what you find is your difference in energy is going to be something around 790.5. This can fluctuate between 786 and 794 depending on how many decimal places you drop or keep in all these answers up here. So essentially, that is the change in kinetic energy. So notice, in this case, the kinetic energy actually dropped because this is less. So you cannot have a gain in energy. So this should always be a positive value unless energy was added to the system. But in this case, energy wasn't added to the system. So you actually lost some energy. And to account for that energy, you know that every time two bodies stick together, you can lose energy, either sound, heat, or the energy that you need to actually get those bodies to stick together. So that accounts for the difference in energy between these two. And that should be the whole problem.